This is AP Calculus BC, Unit 5, Objective 2, and we were dealing with inverse functions in Objective 1, and then we also had a review of some inverse trig functions, but now we're actually going to be doing calculus with them. And now that we're actually through the first 4 units of calculus, first 2 units, derivatives and applications, and then the next 2 units, units 3 and 4, integrals or antiderivatives and applications and all that kind of stuff. So now we're past the basics of all those, and so now we're starting to get to more of the transcendental functions is what they're referred to as, because they transcend the more basic ones. And anyway, derivatives and integrals and limits will all be coming at you at the same time, basically. So we need to be ready for that. Okay, so derivatives, and yes, the coloring has something to do with it too, so we do want to notice that. So the derivative of inverse sine of u is 1 over the square root of 1 minus u squared times the derivative of the guts. Okay. Now notice the only difference between the derivative of inverse cosine and the derivative of inverse sine. A negative, that's the only difference between the derivative of inverse cosine compared to the derivative of inverse sine. Derivative of tangent, inverse tangent, that is, 1 over 1 plus u squared times the derivative of the guts. And the derivative of inverse cotangent, negative 1 over 1 plus u squared times the derivative of the guts. So I'm sensing a theme here that the inverse trig functions that start with a c, the only difference is when you do the derivative, you got a negative, and really that's what's happening. And so we want to take advantage of things like that and notice that situation so that we don't have to memorize everything so disjointly, and then it's hard to keep track of everything. Okay, now, much like when we were doing integration with trig, we're not dealing with polynomials here and integrating polynomials. So the key to integrating when you're dealing with the inverse trig stuff is to know your derivatives. And so the integral of du over the square root of 1 minus u squared, or in other words, 1 over square root of 1 minus u squared. And this is all reliant on the fact that you can actually see the derivative of the guts right there, or you can make adjustments for it. So that's going to be inverse sine of u plus c. By the way, if there's a negative there, then you can just have the negative out in front, and it's negative inverse sine of u. Or you could actually say that it's inverse cosine of u plus a constant. But really, we had 6 formulas for derivatives and just 3 for the integrals. The integral of du over 1 plus u squared, that's inverse tangent of u plus a constant. And the integral of du over u times the square root of u squared minus 1, that would be inverse secant of u plus c. But it is possible to also write it as inverse cosine of 1 over u plus c. Okay, so let's do some examples here. I've got 6 examples. So the first 2 are just derivatives. And so here's y equals, and I want dy dx. Okay, so really all you're doing is you're doing the derivative both sides with respect to x. Okay, so we have dy dx. Well, let's see, it starts with a c. Okay, so it's going to be negative. I know it's going to be negative. Okay, and so negative 1 over, okay, now let's similar to the tangent. So it's 1 plus the u squared. Okay, so my u is root x. So if I square that, that's x times the derivative of the guts. Okay, now the derivative of the guts, the derivative of square root of x. Now square root of x, we've been doing that for a while now. So that's 1 over 2 times root. And the derivative of the inside guts with respect to x is just 1. So we get negative 1 over 2 root x times 1 plus x. Okay, and I suppose you can you could distribute the 2 root x, but really that doesn't help clean it up any at all. So I'd probably just leave it like that. Okay, number 2 here. Again, looking for dy dx, so I'm going to take the derivative of both sides with respect to x. Okay, so I've got dy dx. Okay, product rule here first. X times inverse cosine of 2x. So first times the derivative of the second. Okay, so inverse cosine negative 1 over square root, okay, 1 minus the u. Now the u is 2x, so 1 minus u squared. So if I square that, I get 4x squared. Okay, times the derivative of the guts, okay, which is 2. Effectively, that goes to the numerator. So it's like you might want to go ahead and put it up in the numerator immediately, but it's notes. I'm showing each step here right now. So product rule. So that's the first times the derivative of the second plus the second, which is inverse cosine of 2x times the derivative of the first, which is 1. Okay, so that's the product rule of that first. Okay, now this second part, not a product rule of variables, so it's not going to be the product rule for derivatives. But let's see, I do have negative 1/2, and then, okay, it's a square root function, so 1 over 2 times the root thing, times the derivative of the guts. Okay, the derivative of the guts would be negative 8x. Yes, we do need to fill in the square root. Okay, so if we clean this up, we've got negative 2x over square root of 1 minus 4x plus inverse cosine of 2x. Here's a minus 1/2 times and times, and there's another minus, so it's a plus. And let's see, the 2's and the 8's are actually going to reduce, so that 2 reduces there and reduces there, and then this 2 reduces with that and reduces with the 4. Okay, and so now I have negative, sorry, it's not negative, it's positive. Positive 2x over square root of 1 minus 4x squared. Oh gosh, let's look. The first term here and the last term are opposites of each other. So those two eliminate each other. And we are left with inverse cosine of 2x. Okay, so first two were derivatives. Now we're going to do a couple of integrals, and they might be indefinite integrals, or they could be definite integrals. So we have to be able to adjust to either. Okay. Now, which one is this one reminding us of? And when we have the square root here, it's important to pay attention to whether it's the variable minus 1 or if it's 1 minus the variable. So this one's the variable minus 1. because you can't just look at the thing out in front and say, oh, well, this is obviously the inverse secant thing. I would focus on the inside of the radical more, because sometimes the thing that's out in front of the radical is actually part of the du. So anyway, this is u squared minus 1. Okay? Now, what I have found over the years teaching this, the integration of the inverse trig stuff, it's so easily messed up. And I think it's a good idea to match it up to the formula exactly. And so in this case, the u would be x. And so the du would be dx, okay? And so really it's a very straightforward substitution. I mean, you wouldn't really have to do this one as a substitution because it just matches up so perfectly. But if you wanted to really match it up here, you would go ahead and bring the 3 out in front. And we have -2, negative root 2, and we have du, this is the dx, and this is u square root of u squared minus 1, and this is what I'm talking about. Really, it's like, it's basically, it's the same exact problem we just had, so you don't really have to do the formal u substitution when it's this straightforward. But anyway, if we go ahead and do that now, so this is definitely matching the inverse secant, and so this is 3 times inverse secant of u, okay, and we don't have to worry about the plus c because it's a definite integral, but remember, if it's an indefinite integral, don't forget about the plus c. Okay, so we have 3, and then I would have inverse secant of, now it's going to be absolute value of negative root 2, so really it's just root 2. Okay, and I might even write root 2 over 1. Minus, and then I'm doing absolute value of the negative 2 again, so it's really inverse secant of 2 over 1. Now, I don't think as well in secant as I do cosine, inverse cosine. So, and then this is where it's kind of handy, where inverse secant, inverse cosine, they really have the same boundaries, quadrant 1, quadrant 2. And so, as I'm doing this one, I'm thinking to myself, okay, so what is the angle? Because that's what we do when we're doing the inverse trig stuff. So what is the angle that has a cosine of 1 over root 2? Okay, well that's pi over 4. Minus, okay, what is the angle that has a cosine of 1 over 2? Okay, well that's pi over 3. Okay, and so now common denominator, it's 12, so that's 3 pi over 12 minus 4 pi over 12. So we have 3 times negative pi over 12, which is negative pi over 4. Okay, moving on. Number 4 here. Now, this is one that maybe it's a little bit better idea to go ahead and do a u substitution here. For example, look, I mean, some of you are going, what the heck is going on here? But which one does this most remind us of? I mean, yes, there's a square root here, but there's no 1 minus or x squared minus 1 or anything like that. So really, I think this 1 plus x, this is like the 1 plus u squared. So what is the u? If you square it, you get x. So it looks to me like u is the square root of x. Okay. Now, what does the du look like? Because we need to make a substitution. So du du would be 1 over 2 root x dx. And so now we're looking, we're going, oh, that's where that root x comes from, that down there in the denominator. Okay, so we have the 2 that's up top, we can just kind of bring that out in front. So we have 2 integral. Okay, I want to just go ahead and do 1 over, okay, wait a minute here. We had 1 over 2 root x. We see the 1 over root x. I don't see the 2, so I'm going to bring the 2 over. So 2 du equals 1 over root x dx. Yeah, I like that better. So we can substitute for the 1 over root x dx, and we can substitute it 2 du. Okay, so the 2 du, that's this part right here. So I've got 2 and du. So the other 2 is the 2 that was in the numerator, and then the 2 du is replacing the 1 over root x dx. Right there. Okay, so moving on. Now that leaves just the 1 plus x, which is 1 plus u squared. Okay, and our limits of integration. Okay, so in x land, 1, so plug in a 1, square root of 1 is 1, and 3, square root of 3 is square root of 3. Okay, so this is 4 times inverse tangent of u evaluated from 1 to root 3. So we have 4 times inverse tangent of root 3 over 1 minus inverse tangent of 1. Okay, so what is the angle that has a tangent of root 3 over 1? Okay, well, that's pi over 3. And what is the angle that has an inverse tangent of 1? Well, that's pi over 4. Okay, so 4 pi over 12 minus 3 pi over 12, that's pi over 12. So I've got 4 pi over 12, which reduces to pi over 3. Okay, so that was 2 integrals. Now we've got our limit. Actually, 2 limit. Well, 1 limit and then 1 to solving a differential equation. Sorry. Okay, so limit as x goes to infinity. Well, let's see. As x is going to infinity, well, this is just kind of a mess. Unless the top is in factored form, so I could move something to the denominator. Now, I know that it says tangent to the negative 1 power of 3x, but really that's notation for the tangent of negative 1. Remember, we talked about that in objective 1. It's not actually a negative 1 power. It means inverse. So if we moved it to the denominator, it's just a mess. It's not tangent of 3x. What we do want to move is we do want to move the x to the negative 1, because if we move that down to the denominator, it just becomes just x. So that's what we're going to move. So we've got limit as x goes to infinity. And so I'd have 5 times x in the denominator. And up top I've got 2 times inverse tangent of 3x. Okay, now, there was one graph I told you guys you absolutely have to know as x goes to infinity. Okay, and I wrote down the problem incorrectly. I was all of a sudden, I was getting worried because I was going, this is not working out the way I was thinking. It's not supposed to be limit as x goes to infinity. So it is supposed to be the limit as x goes to 0. Now it makes a lot more sense. Because if we're going to be doing the limit as x goes to infinity, inverse tangent of 3x, that was going to be going to pi over 2. And this was not going to be the situation that we wanted. So I'm sorry, it's supposed to be limit as x goes to 0. Okay, so let me fix that over here as well. Okay, limit as x goes to 0. So I notice my denominator is 0. So I'm kind of really hoping my numerator is 0 so that I can use L'Hopital's since I'm noticing my denominator is 0. And so let's see, 3 times 0 is 0. So what's the angle that has a tangent of 0? 0. So this is 0 over 0, which means we get to use L'Hopital's. So remember to advertise. And it's not going to infinity. I've got that one kind of locked into my head now, evidently. Okay, so derivative at the bottom is 5, and the derivative at the top is 2 times, okay, well, inverse tangent. So 1 over 1 plus the u squared, so 3x squared is 9x squared times the derivative of the guts, derivative of the u is 3. Okay, so this is the limit as x goes to 0. Okay, so I have 6 over 1 plus 9x squared. And that's 5 over 1 on the bottom, so I can multiply by 1 over 5. Okay, so as x goes to 0, well, I can just plug in 0 now. So I get 6 over 1 times 1 over 5, which is 6/5. Okay, so, yep, L'Hopital's is still very handy. I'm going to keep that ready to go. Okay, last problem here for the notes. Solve the differential equation for y if y equals 0 and x equals 0. Okay, now solving differential equations. Remember, the first thing we always have to do is to show separation of variables. And you don't necessarily need to show all the steps to get there, as long as you do it accurately, but you do need to show separation of variables. So I would want to move the square root of 1 minus y squared over to the left, and the square root of 1 minus x squared to the right. So and I can't just put it like that. Over here, this would be 1 over root 1 minus y squared, and the other side would be 1 over root 1 minus x squared. And then I need to move the dx to the other side. So 1 over root 1 minus y squared dy equals 1 over root 1 minus x squared dx. Okay, so that's my separation of variables. Now I need to make sure that I show proper calculus symbols, which I have most of them here right now, but the other thing that we need are the integration symbols on both sides. So it's not enough to just get the correct answer, you need to show the correct work too. Okay, oh look, I think I recognize this. Okay, so this is inverse sine of, okay, so 1 minus u squared, so my u is y, so inverse sine of y plus a constant, but I'll move that to the other side, and the the other side is the same sort of thing, only this time it's the inverse sine of x. And now don't forget the plus c on that side, because they are indefinite integrals. Okay, now it says to solve for y. Now we could solve for y on both sides, because I can do the sine of both sides, but a lot of times when they give you this extra information, like this right here, y equals 0 and x equals 0, it might be actually easier to solve for the c before you do it. I don't know, it just kind of depends. You kind of look at the situation, see what's going on. So I kind of like the idea of plugging in those values right now. Okay, what's inverse sine of 0? What is the angle that has a sine of 0? 0. So 0 plus, so c is 0. Okay, so c is 0. Okay. Okay, so we've got inverse sine of y equals inverse sine of x. And I want to get y all by itself. Well, what's the inverse of inverse sine? Sine. And so